My name is Matteo. I'm with the Gray System Labs in Microsoft. And today I'm going to talk to you about tensor query processing. Pretty much we are trying to leverage AI investments also for database analytics. So I'm a database researcher, so I'm going to give you a perspective for someone that is outside the machine learning community. So basically what we see are two macro trends. So one is there is a lot of dollars that be spent on special hardware for AI. We see startups such as Manova, Celebras. We see hardware vendors such as NVIDIA, AMD, as well as cloud providers that are investing their own custom chips. On the other side, on the software side, we also see a lot of investment from in this large open source community. So we see a really large community related to PyTorch, Onyx Runtime, Hugging Face, etc., etc. And one thing that we find interesting here is that we see a really interesting virtuous cycles between researchers that create new machine learning models, engineers that make them run efficiently, and hardware vendors that try to run them better on their hardware. And this is kind of different than what we see from the database community, where we have hardware investments, but these in general are way more modest compared to what we see in the AI space. And this is mostly because everyone is trying to map their own SQL operators into different hardware, and this is a really large problem if you want to support hardware for different vendors. And everyone is building their own custom implementation for those. So our idea for the Tensor Query Processor is quite simple. So we basically want to do the same things that machine learning engineers, data scientists are doing these days with systems such as PyTorch. So what we see them doing is basically they implement their machine learning model using this Pythonic tensor interface that is really high level, and then they use these tensor runtime such as PyTorch to kind of map their high level kind of Python programs into something that can be executed on the hardware accelerators. And we pretty much want to do exactly the same for relational SQL queries. So can we basically map SQL into the similar tensor abstraction, and by doing so, we can basically as well leverage hardware accelerators kind of for free. So this is kind of strange ideas and why we even think that this can even work, right? So actually, before this project, we started a project that was called Hummingbird. Hummingbird is open source. It's actually part of the PyTorch ecosystem. And what we were doing with Hummingbird is taking trained classical machine learning models, such as the one that you implement using scikit-learn, XGBoost, etc., and translate this model into PyTorch, and by so run them on hardware accelerators. And with Hummingbird, we actually got some really interesting results. Like by then, I think we pursued around 2020. For certain XGBoost models, we were faster than the custom GPU implementation of XGBoost. So for us, it was kind of, okay, we think that kind of this approach might work. And with TQP, basically, we moved to the step 4. They kind of say, okay, beyond classical ML, let's try to see if we can also do the same trick with relational SQL queries, and by so run databases over hardware accelerators. So there are two things here that I want to show you. Basically is, since we are talking about tabular data, how we can represent tabular data into tensors, and now we can go from SQL query into something that can be executed on hardware accelerator through PyTorch. So for the first part, is actually quite simple. So we basically look at the tabular data from a columnar point of view perspective. So each column is kind of is separate, and if you see from this point of view, basically each column you can see it is a tensor. Like the first two columns are numerical columns. So those basically can be mapped to one-dimensional numerical tensors. The third column is date. You can basically translate the dates into timestamps. So you also have a numerical column. For region, that is a string. What we do is really naive at the moment. So we just map that to UTF-8. So there will be a two-dimensional tensor where one dimension is kind of the maximum number of strings that you have in each row, and then kind of how many strings you have. We have a more optimized way to encode this, but this is to give you an idea that it's not just beyond kind of numerical columns. And by embracing basically tensor as kind of our data representation, we can also represent other modalities in databases. So we can load images because they're just three-dimensional tensor. We can load audio, et cetera, et cetera. So we're going even beyond what the relational database can do. Most of relational database can do nowadays. Next, about how we go from SQL queries into something that can be executed on hardware accelerators. So we start with the SQL query. We have a parse and optimizer step that basically use external systems such as Apache Spark and SQL Server to take the SQL query, parse it, optimize it, and generate a physical plan composed by physical relational operators. So this plan is just a DAG, right? Then we have a converter step that basically convert this physical plan output by SQL Server and Apache Spark into our own in-memory representation. And then the next step is a tensorize that basically for each of the physical operators that we have into this DAG, we have a corresponding PyTorch tensor program that basically implemented the exact same algorithm but in tensors. So we cannot swap each of the physical operators into a PyTorch program. One thing that I want to highlight here is that our initial prototype, we only used like PyTorch, but that was not giving us a good performance. So we also had to implement some custom operators for something like joins or group by to kind of have them run faster. So at the end, after the tensorizer, we basically have just a list of PyTorch programs. So pretty much we are in PyTorch land that we can run on any hardware accelerator that PyTorch support. One additional step that we add at this point is fusion and code generation. So when we started this project, there was no compile API. So what we use is Antares Auto-RT, which is an open source Microsoft project, and is a state-of-the-art operator fusion for tensor programs, as well as allow us to generate code also for other devices now that are not supported by PyTorch. For instance, with Antares, we can run PyTorch program and SQL program on Xbox by targeting DirectX, for example. So pretty much at the end, as I tell you at the beginning, we can transform like tabular data into tensors. I explain right now how we can transform SQL programs into PyTorch programs plus custom operators. So we're basically in PyTorch land. We can execute as it was a PyTorch model on any hardware device that is supported either by PyTorch or Antares. Finally, I want to talk a little bit about performance. How does this work? So in the database world, for analytics, we use often TPC-H as kind of a standard benchmark. So here I'm going to show you how we can run TPC-H scale factor 50. We compare with CPU database, state-of-the-art CPU database such as SQL Server and Databricks. And for those, we basically run on an Azure machine with the 64 logical core, and which is about 50%, to give an idea, is about 50% less expensive than any 100. And as you can see from the numbers here, by just doing this simple trick, we can basically run SQL queries on PyTorch, and we are already around 4 times, on an E100, we're already about 4 times faster than SQL Server that is kind of state-of-the-art, enterprise level databases, and more than almost 2 orders of magnitude faster than Databricks. Then if we add fusion on top of it, so if we use Antares to do fusion and code generation, we can add another 4x on top of it. And of course, we are on PyTorch, so we can just swap the GPU that we are using to the newest one, such as an A100, and this gives us a total of, say, 6.6 performance improvement compared to the original numbers that we are getting. So at this point, we are able to run the full TPC-H scale factor 50 in 0.33 seconds. This pretty much is the end of my talk. So this is, of course, I'm here presenting. I'm Matteo, but this is an effort from a large team at Microsoft, and I want to acknowledge them here. And if you're interested on the specific of what I just presented, we have already published a bunch of papers, so you can go there and check them out. And I think we have some time for a few questions if someone want to ask some question. Thank you. These are really good questions. So I don't have the slides here, but of course, we did all our internal kind of benchmarking. And as you can imagine, like in this case, let me just bring this up. Like, if we take the A100, we are about what was 16x, I think, compared to SQL Server. If we use Fusion, etc. And this an A100 virtual machine on Azure is about 50% more expensive than the CPU machine there. So we still have kind of a large margin there for the cost performance basis. And of course, that is what interested us as a cloud vendors. We want to make sure that not just we're fast, but also our the performance and cost are positive for us. Yeah, thanks. Question?
Numerical queries,
Mm-hmm.
or you can handle even like other forms queries. Like for example, if you're doing like string operations or other things, how well are they?
We support, like, TPC-H contains a bunch of, I mean, it's simple, but not too simple. So it contains strings, and what we do for strings is we have actually two implementations, but the naive one is we just kind of pad them and consider a column string as a two-dimensional tensor containing like a numerical, basically UTF representation for the strings. So we can support strings, we can support joins, group by, if clauses, like statements, and everything that is pretty much needed to support the full TPC-H benchmark. So not just numeric. Timestamp dates as well. We convert into timestamps, so they are numerical. That is what typical databases do anyway. Yeah. Sure.
Question on the benchmark. Can you
Sure.
yeah, here. So the Databricks Fulton comparison here, is the data sitting in the memory already, or it's actually loaded from this?
We warm up. So we do 5 warm-up runs. So we load both from TQP. So we warm up the data set in the GPU memory. For SQL Server and Databricks, we warm up the data from disk to CPU memory. So we kind of warm up the buffer pools, and we make sure that the data set is ready in memory. Yeah.
In terms of memory usage, I know that, for example, SQL Server and Fulton, they probably have a different representation for example, string, watch out, right?
Correct.
So, and in terms of memory usage, it would be TQT consume a little bit more memory. Do you have data on that?
Yes. So I can speak about SQL Server, and I think at Databricks, they have a different data representation. So SQL Server is really efficient on how they represent the data. So we, on our side, we basically represent data as kind of a plain kind of arrays, right? Instead, the SQL Server, they do a bunch of kind of tricks to represent the data in a more kind of compact way. For instance, they look at how many bits you need to actually represent all the values inside one column. So they do all these tricks. But we're working on kind of getting really close to that. So now basically the memory consumption that we have is if you have like plain unpacked arrays, one for each column, plus some kind of overhead for strings because we do padding. But we are working on kind of getting closer to how the data is represented in kind of in real databases, so with a little bit more compact representation. And we think we can probably use still the tensor abstraction also to represent the data in this compact way.
One more question.
Sure.
Is this project available somewhere?
No, unfortunately not. Yeah, unfortunately, is all internal at the moment. We might try to open source something, but since it's still under development and we're working with the product teams, etc., is still kind of it's not the right time for us for open source it right now. Yeah. Anyway. Sure.
Yeah. So are those queries in core, as in like the data set required to answer each query fits the GPU, or
Yes.
in that case where you have to stream through the GPU?
Yes, so we're actively working on that. So we have a version of PyTorch where basically, if we start to have memory pressure on the GPU, we swap the tensor in and out. I think this is common technique in the machine learning space. I found like several papers on this. And we're also working right now on supporting like streaming kind of interface. So you stream in batches of data, you do the query over those batches, and eventually kind of move the batches back to CPU if you're running out of memory. For the numbers that I show, we assume that the data set fits in memory, but we're working on kind of removing this assumption as well. Because of course, kind of, database, you can have like terabyte size data sets, so you need to figure out a way to support them so in smaller GPUs. Yeah.